linear dynamics now. Okay, let's just try to do it. So it's negative CAR x plus V divided by this Bm. Okay, please pay attention. And I will substitute my feedback into here the open loop, which means I will get what? If you substitute the feedback, you get what? The closed loop system, right? So the closed loop system is x dot equals a x plus bu, so a plus the b times this guy, so this is actually b car divided by this is scalar, this is a matrix times x plus b times u, so again 1 over bm, b as a column, v, and y is cx. So all what I did is just I introduced this control law, which coming from our philosophy of input-output linearization, feedback linearization. Okay, I just introduced this control law, feedback. Here's the feedback gain, CAR, and so you get a new closed loop transfer function. You probably feedback moves the poles, right? So I'm asking you, what is the transfer function y over v? Now, what's that? Do you know the relation between y and v after we do input-output linearization? What's the relation between y and v? What is y by the TR? What's that? After we do our process, it's v, right? Yeah. So the r time derivative of y is just v. So what's the transfer function? When you take the Laplace transform here, what's the transfer function? If it's y dot equals v, what's the transfer function? If it's y dot equals v, what's the transfer function between y and v?
SV.
It's 1 over s. Yeah, right, 1 over s. So, and if it's y double dot is 1 over s squared and so on and so. So the r derivative, this is 1 over s to the r, right? This is the closed loop transfer function. Okay, so I had my, the poles from the beginning of the system, which are, I have n poles, right? It was an n order system, n poles, which are the eigenvalues of the A matrix. These are the open loop. After feedback, the feedback affects the poles but doesn't affect the zeros. Okay? Okay, so I had n poles. Now, they are just R poles, right? At s equals 0. So where are the rest? Where they have gone? Where they must have gone? If this is the case, I'm telling you here, I have n poles and m zeros, where n minus m is r. Okay? So let's give an example. This is 10 poles, and I have 7 zeros. Okay? After I do this feedback, I have 3 poles. So what do you conclude? Where are the rest 7 have gone? Again, 10 poles and 7 zeros in denominator and numerator. You did feedback. The feedback affects the poles but not the zeros. The zeros will remain. So here we have 3 new poles and the 7 have gone. Exactly, they are the locations of the zeros. So they cancel each other. Okay? So this must be an n minus r, which is m poles at the location of the zeros of the original system. Okay? So they cancel each other, which means we have pole zero cancellation. And if you take 270A, they are really obsessed about the pole zero cancellation because it causes what? Either uncontrollability or unobservability. Okay? Here it changes, feedback doesn't change controllability. This is actually a typical question in the prelim in linear control theory. They keep playing with this language. You do feedback, and there is pole zero cancellation. We know that the feedback doesn't change zeros and changes pole. We know that the feedback doesn't change controllability, but may change observability. If there is pole zero cancellation, it's either unobservable or uncontrollable. So the conclusion of this whole story is that it's unobservable, because controllability cannot change under feedback, right? This is a typical question in prelim, okay? So pole zero cancellation, it leads to the unobservable dynamics. This is why we have the unobservable part, and just demonstrated it here using linear systems. Any questions so far? So it's as if this control law star, that we will always apply for linear systems, it places M of the poles at the zero rotations. It does intentionally pole zero cancellation to do this decoupling. Okay? So that's okay about the pole zero cancellation and the unobservability. We didn't discuss the minimum phase system yet. What is the relation between this concept of the zero dynamics to be unstable with the non-minimum phase when the zeros in the right half plane? So let's do it now and we'll finish the lecture by then. Any questions so far, please? Any question? So G of S, this is your transfer function, which is numerator divided by the denominator. This is of degree m, this is of degree n, right? I can write d, say divided by n, so the reciprocal of the transfer function, because d is of higher degree, so I can divide by. If you divide by, you get a quotient and remainder, right? What's the degree of this guy is the difference. So it's n minus m, which is r, okay, the relative degree. And the degree of this guy is less than n. Okay, so actually I can write down my transfer function as 1 over this guy, 1 over divided by n. So 1 over q plus r over n, okay? So it's 1 over q divided by 1 plus. So it is in the favorable form of g plus divided by 1 plus gh, right? Something like that. So it's we have a plant. Now we have the feedback h something, and we have this guy. So here goes 1 over q, here goes r over n. Do you agree that this is exactly equivalent to this block diagram, where this is y, u, between the input and output, okay? And I'm going to call this, say, error, and this anything, W, say, okay? My claim is, of course, this is a contrived construction, so we made it intentionally. My claim is that this is the psi dynamics and this is the phi dynamics, and I will show you why. So this is the psi dynamics and this is the phi dynamics. First of all, it seems a little bit intuitive. Why? Because Q is degree what? Is degree R, right? My psi dynamics is degree R indeed, right? And the phi dynamics is unaffected by the input. It depends just on the output, which is the psi's. Yeah, phi dynamics depends on the psi's, that's fine, and doesn't see the input. So from the beginning you have an intuition, but we need to show more features. So let's write a state space form for this block only, 1 over q, and the state space form for this guy only. Okay? And to prevent confusion, obviously I will call the states here psi's, the states here phi's. Let's write a state space form, please. So realization of 1 over q. State space form, x dot equals ax plus bu and so on. So my states are psi's, like I said, I'm going to call them psi's. So this is here some A matrix times psi, okay? Plus some B matrix times the input. What is the input of this block? E. And the output of this block, which is Y, is some C matrix times epsilon. Where again, as usual, A is my controllable canonical form 010s, 001s, and here the coefficients of Q. The coefficients of Q, right? the coefficients of the denominator. B is 0, 0, 1s, and C is usually the coefficient of the numerator of the transfer function. The numerator here is just 1. So this is 1 and zeros. This is R by R, okay? Because Q is Rth order system. And let's do the R over N. Before doing R over N, just to, because this is in this form, whenever I multiply C times B, I get 0, of course. And we said before that A times B just moves this guy 1, right? So whenever you move it, this is all zeros, so just when it comes here, it can give you just a unit, a non-zero number. And it comes here after multiplying A by R times. So just before going, we know that dRy by dtr is CAR epsilon plus CAR minus 1B times your input, which is E, and this is kind of unit or something. So E, I'm reminding you, E from here is U minus W, right? From the block diagram. Okay, let's do realization together to the R over N. So let's do it, please. So phi dynamics, phi dot is some A matrix, I'll call it A naught, times the phi, plus some B matrix, it's B naught, times its input. What is the input to this block?
Y.
Y, very good. Okay, and its output, the output of this block is just W, so it's some C times the states, okay? One thing here that I want to know that is very interesting. What is the eigenvalues of A naught? What are these? Forget anything else. This system, the blue system, is a realization of this transfer function, R varied by N, okay? So what is the eigenvalues of X matrix? They are what, by definition? Without anything that you got this lecture, this is just the general information. This is a realization of a transfer function, R over N. The eigenvalues of this guy is what? How it's related to the transfer function? How the poles of A are related to the transfer function? The eigenvalues of A matrix, how are they related to the transfer function? What are the eigenvalues?
The poles.
The poles. The eigenvalues are the poles of the transfer function. And what are the poles? What are the poles? What are the poles of the transfer function?
The denominator.
The roots of the denominator. Those are the roots of N, right? N for the original system is what? Is the numerator. So the roots of N are what for the original system? Zeros. The zeros of the original system, okay? So actually, for the phi dynamics, the eigenvalues of the phi dynamics are the zeros of the original system, okay? So this is an important thing that actually this will be the main result here. So let's write down the combined system, the combined. What's the combined system? We have from here epsilon dot is A epsilon plus B times E, which is U minus W. W is C naught phi. The phi dynamics is another A times phi plus B times Y, and Y is C epsilon. So this is a state space between phi and epsilon. Its output is just the Y which is C times epsilon. So so this is C naught phi. What is our usual law? We do it here by cancelling all the other terms, right? So U is C naught phi plus, this is actually Bm. So 1 over Bm negative C AR epsilon plus V. So this is our controller that we kept saying this is a star. So when you do star here, how the epsilon dynamics would look like? They will look like this: psi 1, psi 2, or actually 0, 1, 0, 0, 0, 1, and yada yada. We have here 1, we have zeros here, right? Psi 1 up to psi r, psi 1 up to psi r, plus 0, 0, 1, and V. The star doesn't affect here at all, so this is on its own. Phi dot is A naught phi plus B naught C epsilon. Right? So for linear systems, this is the transformed thing. Okay? Our epsilons and our phi's. What is the zero dynamics? Can you tell me what is the zero dynamics here? What is the zero dynamics? By definition above, what is the zero dynamics? You put what equals 0? So here we have complete authority over psi. We're just afraid that this thing blows up, right? So we want to make sure that when psi is 0, this is okay. So the zero dynamics is, so by 0 we mean psi is strictly 0, and we're focusing on the unobservable dynamics, right? You can see that the zero dynamics is stable from just this picture. If what happens? The eigenvalues, very good, are in the left half plane, which means what? The zeros of the original system, right? In the left half plane. And zeros of original system in the left half plane, this is the minimum phase concept in undergrad. This is just the minimum phase concept for nonlinear systems. Is that we don't have poles and zeros, but we have the zero dynamics and we can check if it's stable or not. Okay? They are equivalent poles. So this is the minimum phase concept, the general concept.